Oh, all right, everybody, welcome back. Today we're going to be doing section 7.7, which is all about approximate integration. This section is actually a pretty interesting one because approximate integration is still an active field of applied math research. So if you get into the things that we're talking about today, you might find that you want to get into them even further later on when you get into your upper division courses or even graduate level courses. Let me pull up the slides and we'll get started. Okay, so one thing I've got to say at the beginning here, just a fair warning, this is a bit of a long section. So as you can see, there are quite a bit of slides in this particular section. There's 53. If you need to take a break in the middle, that's totally fine. Take a break. The reason that this one is so long is because there are a lot of different approximation methods that we're going to explore, and then we have to explore error bounds for those approximation methods. So in the very beginning, what we're going to do is we're just going to revisit the mechanics of the Riemann integral again, just to see what exactly is going on with the Riemann integral one more time. I know we've seen it a bunch of times, but we're going to look at it again. Then we're going to talk about four different, or really, what is it? One, two, three, four, five different integral approximation methods. So left and right endpoint approximation, midpoint approximation, trapezoidal approximation, and quadratic approximation. Once we have gone through all those approximation methods and done an example or so for each one, then we'll talk about the error bounds that are associated with those methods, basically how far off they are. Okay, so let's go back to this. So remember that the definite Riemann integral of a function is basically the area under the curve of that function. And in a lot of cases, you can just find an antiderivative of that function, use fundamental theorem of calculus part 2, and then compute that integral to get an exact value. But there are many, many integrals that don't have an antiderivative in terms of elementary functions. And a classic one is this one, which is related to the Gaussian, or just like the Gaussian distribution. This function here, e to the negative x squared, doesn't have an elementary antiderivative, but we would like to be able to evaluate expressions like this. We want to know the area under that curve from 0 to 1. The downside is we can't use FTC2 to do so because we don't have an elementary antiderivative. But that doesn't mean that we can't get at the integral itself, and that's something that we saw in an earlier section as well. The other thing is this: since we're trying to compute the area under this curve, we can approximate the area using a few different methods, and that's what we're going to do today in today's section. So just a quick reminder of the definition. If you want to define the definite Riemann integral, you start with a function that's defined on an interval. You partition that interval by selecting a bunch of partition points within the interval, where the first point is the left endpoint and the last point is the right endpoint. Then we define the definite Riemann integral of the function over this interval to be the number represented by this symbol. So remember, when you see a definite integral, it is a number. It is a specific number on the real line. We could point to it. How do we define it? Well, it's the limit of this sum, the limit of this Riemann sum. And delta x sub I is just the distance between the partition points. And f of x sub I star is the height of the function at some sample point, x sub I star. And then we add up all of those areas. Remember that this piece right here, that's the area of a rectangle. We're going to add up the area of those rectangles, and then we're going to take a limit as the biggest interval goes to 0. Now, if this limit exists as a finite number, then we say that the function is Riemann integrable over this interval, and we get the integral. The integral is this actual number, the limit that you get. So here's the picture that you're usually associating with this. Again, you partition your interval using a partition of your choice. Doesn't really matter what the partition is. You get to pick what the x sub i's are. And then within each one of these little subintervals, you're going to pick a sample point. And that sample point is the one that we star. So we call it x sub I star. That's this guy right here, x sub I star. So in each subinterval, pick a special point, x sub I star. And then you evaluate the function at that point. And basically you just take the height, right? The height, or I should say, maybe I'll do this right here. You take this height. That is the value f of x sub I star. That's what you get right there. And then you can find the area of the associated rectangle because the area is just this height times this width, and then you add them all up. That's the idea. Um, by doing that, or I should say this, so the actual, yeah, let me go back. Here you go. The actual integral itself is equal to the limit of these sums. And the limit is taken as the intervals shrink to nothing. So that is the equal, like the equality there, that's the integral itself. But if you don't shrink the intervals to zero, then you get a relative approximation of the integral. So here we're not taking a limit, we're just adding up a finite number of areas. And that number that we get is, it's about it's about the area under that curve. That's why we have this symbol here to indicate an approximation. So remember, the equal sign is a sacred symbol, so you can't abuse the equal sign. Equal means that the two things are the same, that they have the same value. In this case, these two things do not have the same value. This thing is just close to this thing. What does close mean? Well, that's what we're going to talk about today. Uh, a lot of times what we'll do is rather than dealing with subintervals that are of different size, a lot of times we just choose the subintervals to be the same size. And the way that we do that is we take the length of the interval a to b and we divide it by n. And n is just the number of rectangles that we want to use. So they don't, the partition and the subintervals, they don't have to be uniform, but they can be. And so a lot of times we just do that to make our lives a little bit easier. So now you'll notice that we don't need to refer to delta x sub I, where delta x sub I depends on the interval you've chosen. Now we can just say all the intervals are the same length. So there's a single value delta x, and each one of these subintervals is the same length, right? Okay, so our integral will be approximately the sum of the area of those n rectangles. Okay, now let's talk about approximate integration now that we've kind of seen the mechanics of the Riemann integral again. So first we got to talk about approximations of functions. So there's two different approximations that are going on in this section. There are approximations of functions, and then there are approximations of integrals. So there's a distinction between these two things, and there's an interesting relationship between the two. So what is a zeroth order approximation? I know that sounds kind of funny, but we've been looking at them. We've been looking at them in the previous slides, and you've been looking at them for a while. So a zeroth order approximation is just a constant approximation. In other words, it's a polynomial of degree 0. So polynomials of degree 0 are just real numbers. So they're horizontal lines. So in other words, the function f is approximated by a horizontal line, y equals c, so that our function is about the value c on some interval. So that's a zeroth order approximation, a constant approximation. Okay. Now, the standard mechanics of the Riemann integral involve using a zeroth order approximation of a function, and the approximation is determined by your choice of sample point x sub I. So if I go back to that picture again, this one right here, these horizontal lines, those are zeroth order approximations of the curve at those sample points here. So we pick those sample points, we compute the height of the function at that point, and then we just draw a horizontal line at that height over the entire interval. That's a zeroth order approximation of the function, and then we use that to get an approximation of the integral of that function. So let me go back to this now. So first of all, this is not the only way to generate an approximation of an integral, and that's one of the things we're going to explore in today's lesson. And also, with any approximation, there's an error produced. These are not equalities, these are approximations. And it turns out that the choice of sample point that you make affects the size of the error when you want to approximate the integral. So sometimes there is a better choice of x sub I star, and how you choose it changes the approximation and it changes the accuracy of the approximation. Interesting stuff. So what we're going to do now is we're going to explore 3 different integral approximations where we use a zeroth order function approximation each time. And that's what we're going to do. So we'll get 3 different horizontal line approximations, and that'll give us 3 different integral approximations. So here we go. Here's the first 2, left endpoint and right endpoint approximations. So first we're going to do is we're going to choose our sample point to be the left endpoint of this subinterval. So for each subinterval, we're going to pick the left endpoint. So that means that our sample point is x sub I minus 1 for I equals 1 to n. Then what we have is that our integral is going to be about the value of this left endpoint approximation, which depends on the number of subintervals, L sub n. So notice here, it's the same structure as the standard Riemann integral, right? Except now we're evaluating the function at the left endpoint, and we're doing that n times. So L sub n is what we call the left endpoint approximation of the net area under the curve of y equals f of x. And this is a picture of what it looks like. So you notice here what we're doing is our sample points are the left endpoints. So what we do is we evaluate the function at these left endpoints, and then we produce a 0th order approximation of the function based on those left endpoints. And then we find the area of these rectangles, and then we add them up. And if you look at this picture, you can see that the sum of the area of all these rectangles is definitely not equal to the area under this curve. Definitely not equal, but it might be a decent approximation if you can kind of like play with it in your head. And maybe if you could move this region that's above the integral and put it under here, it might actually be pretty close to what the integral really is, what the actual value really is. So that's kind of what we're doing here. Another thing you might notice is, and from previous as well, is that as the number of subintervals increases, your approximation will get better and better. Here we just used 4. We used 4 rectangles to approximate the area, but we could use as many as we want. We could use 1 billion if we want. It really just depends on your problem, the context that you're working in, and how accurate you need things to be. Now, one last bit, a formula to find all of these endpoints is given right here. So in other words, our sample points x sub I star are going to be chosen like so. It's you start at A, the left endpoint, and then you're going to add delta x this many times. So in other words, you start at A, and then you add delta x once to get to x1, you add it twice to get to x2, you add it 3 times to get to x3, and so on. Right? That's the idea. So that's what this formula is telling you. This formula is telling you how to find those endpoints. All right, that's a left endpoint approximation. Now let's look at a right endpoint approximation. So the setup is basically the same. We're still using a 0th order function approximation, but now we're going to pick the right endpoints instead. So our sample points x sub I star are now going to be x sub I, the right endpoint. Just like before, we get an approximation, and this is called the right endpoint approximation of that integral right there. Here you can kind of compare the picture here to the picture here. See, there we go. So now what we're doing is we're picking these points as our sample points and evaluating the function at these points right here, and then drawing a 0th order approximation, and then you find the areas and then add them all up. There we go. Like before, we've got a formula for the endpoints. So the formula in this case, oh wait, there's a typo. My apologies. I'll have to go back and fix this. There should be an I right here. Maybe I'll, here, let me do this. This should be I times delta x. My apologies, I'll fix that. So what do? You start at the left endpoint again, and then you just add delta x to get to the next endpoint. Right? So you start at A, I'm sorry, to get to the first endpoint. Start at A, add 1 to get to the first point, add it twice to get to the second point, and so on and so on. All right, hold on one second. It's a little warm in here. Ah, there we go. Okay. All right, so there's the formulas for those. And now there's a third one. So the third one is a midpoint approximation. So now instead of choosing the left or the right hand endpoints, we're going to choose the midpoint. So our sample point is now going to be the midpoint of this interval. What's the midpoint of that interval? The midpoint is, we denote it with x sub I bar. A lot of times people will use a bar to indicate like an average or a mean or a middle. And then this is the formula for the midpoint. So we take the left and right endpoints, we add them up and divide by 2. That's the midpoint formula, right? So now we're going to evaluate the function at those midpoints, find the height of the function there, multiply it by delta x. That gives us the area of the rectangles, and then we add them all up. That's how it goes. And again, you can compare this picture here. So now what we're doing is we're picking those midpoints, evaluating the function at those midpoints, and then constructing a 0th order approximation of the function there, finding the area of that rectangle or those rectangles, and then you add them all up. So those are the three different pictures. So you got like, here we've got left endpoint, here we've got right endpoint, here we've got midpoint. And so even by looking at the midpoint approximation, it kind of seems like this one's a little bit better than the other two, right? Intuitively, it seems like it would be better, but we got to be careful because sometimes our intuition is not always correct, and we'll see that in this section as well. All right, here's the formula for those points. So if you need to find all those midpoints, you start at the left endpoint A, and then you add delta x this many times, I minus a half times, and that'll basically tell you how to get to these. So to get to the first one, what you do is you start at A, which is right here, and then you're going to add half of delta x. Then you're going to add delta x to get to the next one, and then another delta x to get to the next one, and so on and so on. All right, now let's practice. So let's use the midpoint rule to approximate this integral when n is equal to 5. So we're going to use 5 subintervals, 5 rectangles to approximate this area. Here we go. So we know that A and B are 2. I'm sorry, A is 1 and B is 2. So delta x ends up being 1/5. Remember, we're choosing the subintervals to be a uniform length, so we can find an explicit formula for delta x. It's b minus a over n, which is 1/5 in our case. Now, for I equals 1, 2, 3, ... all the way up to n, we can use that formula for the midpoints to compute the location of all of these points. So the midpoints that we're going to be looking at are given by this formula, which is going to be 1 plus 1/5 times I minus 1/2. And then when you plug in I equals 1, 2, 3, 4, 5, you get these points. So those are the sample points. Those are the x sub I stars. You can think of it like that. So at each one of those points, we're going to evaluate the function to get the height of the rectangle, and then we're going to multiply those heights by delta x, and then we're going to add up all those results. Let's see what we get. All right, this integral is approximately a midpoint approximation with 5 subintervals, and that's given by this, right? It's just delta x times those heights. And then here's where we need to use an approximation. So we have to use a calculator or a computer to approximate these function heights. So that's what we do, and we get this. And then when we add all those up and then divide by 5, we get that value. So there we go. What is this integral equal to? Well, I don't know what it's exactly equal to, but I do know that it's approximately 1.5216. And that's if I use a midpoint approximation with 5 subintervals. There you go. That's the idea. All right, so now we've seen how to use 0th order approximations. Now we're going to talk about first order approximations. So now we're going to approximate the functions with a different type of approximation. How many times am I going to say approximation in this lesson? Like hundreds, I think. Feel like I have to say the word approximation every like 10 seconds. So what is a first order approximation? It's a linear approximation. And this is something that you're all super comfortable with and you've been working with since Calc 1, right? The tangent line basically is a linear approximation of a function at a point. So we usually call that L of x, and L of x is just a line. It's a line, and we can say that the function is approximately equal to that line on some interval. That's the idea. So a standard way to produce a linear approximation is to use a secant line. So rather than using a tangent line, we will use a tangent line later, actually, in section 8.1, which I'll talk about later. We're going to use a secant line. So what we're going to do is we're going to use a secant line that connects the endpoints of the curve on that interval given by these points. And I'll show you a picture right here, actually. Let me flash forward for just a minute. This is essentially how we're approximating the curve, forming that line. So we find these two endpoints and we connect them with a line, find these two endpoints, connect them with a line, and so on and so on. And what that does is it gives us a pretty decent approximation of the function itself. All right, that's the idea. So here's the interesting thing. This will give us a better approximation of the function than a 0th order one will, than a constant approximation. But it does not actually necessarily give us a better approximation of the integral, as we'll see. That's when we get into the error bounds, when we start talking about error bounds and what the errors associated with these approximations are. So now what we're going to do is we're going to use these linear approximations and, and do what's called the trapezoidal rule. So we're going to find the area of some trapezoids instead. Now let's go back to this slide. So geometrically what's happening here is we're just going to use these trapezoids to approximate the area. Oof, that was bad. Let's try that again. There we go. So there's a trapezoid. There's a trapezoid. There's a trapezoid. And then here's a trapezoid right here. All right, there we go. And we're going to find the areas of those. How do we do it? We use the area of a trapezoid formula, 1/2 base 1 plus base 2 times h. Incidentally, if you've never thought about it, this is actually just the area of two triangles. So if you're wondering where this formula comes from, it's because any trapezoid can be decomposed into two triangles, where one triangle has base, one base of the trapezoid, and the other triangle has base, the other base of the trapezoid. So for example, for this one right here, you could just cut it here. And the area of those two triangles will be the area of the trapezoid. Now for our purposes, because our trapezoids are being formed by these functions and these function values, our two bases are going to be given by the function heights. So for example, this would be base 1 and this would be base 2 for this first trapezoid. So base 1, base 2. And then what is the height of the trapezoid? In our case, the height is delta x. And the height is going to be uniform because we chose those subintervals to be uniform. Just rearranging things a little bit, we get this. So this is the formula for the area of the ith trapezoid. So area of the ith trapezoid is given by that. All right. Now, if we add up all these areas, we get an approximation. So our integral is approximately the sum of all the areas of these trapezoids. And remember, delta x and 2, those are constants. They don't depend on I, so we can pull them out of the sum. And then we're just left with the sum of these things. In fact, maybe I should have put some brackets right there. Now, what's interesting is this. So if you write out this sum, just expand it a little bit, you can start to see a pattern. So that's what I've done on this line here, is I expanded the sum out. And check it out. We'll have f of x sub 0 plus f of x1 plus f of x1 again plus f of x2 plus f of x2 again, dot, 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 all the way up to f of xn. So what you'll notice is that each one of these, like these middle terms, is getting doubled. And the reason that they're getting doubled is because they're being double counted from this this setup here. So this one gets counted for this trapezoid, but it also gets counted for this trapezoid. So it gets doubled up. And the endpoints are the end values, those are the only ones that don't get doubled up. That's what's happening here. So those ones, they only occur once, but all the ones in between occur twice. Sorry, that one would be like there. So what's the formula? This is the formula. Delta x over 2, f of x naught, plus 2fx1, 2fx2, 2fx3, dot, 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 2fx sub n minus 1, and then one last f of x sub n at the end. Okay, and that gives us what's called the trapezoidal rule. So this is a trapezoidal approximation of the area under that curve. So if we've got an integrable function, then we can say that the integral is approximately equal to this trapezoidal approximation. Okay, so here's one interesting result. It turns out that the trapezoidal approximation of an integral is equivalent to the average of the left and right endpoint approximations. And we're going to do the calculation right here. But that's kind of it makes sense geometrically and intuitively if you ponder it for a minute. So what I want you to do is just kind of think about for a minute why this picture would be the average of the left and right endpoint pictures. So just ponder that for a minute here. All right, now let's do the proof. Maybe it's not so hard to see that if we took this and found the average instead, that we would basically get this. That's essentially what's happening geometrically. But let's look at the algebra. Remember, a picture is not a proof. A picture is just good motivation. So let's look at the algebra. This right here is the average of those two approximations. Remember, ln is the left endpoint approximation. Rn is the right endpoint approximation. There's two of these approximations, so the average is going to be these divided by 2. Just using the formulas for those approximations, we have that. And then when we start to move things around, you'll notice an interesting pattern. All right, so here, yes, so these are finite sums, so we can do all sorts of interesting things with them. They're really just adding up a finite number of terms, right? So we can move everything around using commutativity, and everything is still good. That's what we get here, times delta x. But remember, we can pull delta x out because delta x is a constant in our case. And then you're left with literally the formula for the trapezoidal rule. Here's the expansion of it, just to really hammer the point home, but that's what you get. And remember, these are all equalities. These are equalities. So what we're saying is that the average of the left and right endpoint approximations is the same as a trapezoidal approximation, using the same subintervals, I should say. And it just depends on what n is. There you go. Interesting, huh? All right, so now let's use the trapezoidal rule to approximate this integral, and we're going to keep n equal to 5. So the process is going to feel very similar. We just have to kind of use our formulas like so, and then we'll be able to get the approximation. Once again, delta x is 1/5 because we're choosing the delta x's to be uniform. Our sample points are given by choosing the left endpoint, and then that's pretty much it. Just pick the left endpoint, so use that formula. When we use that formula, we get this. And then we can just calculate. So we're going to use I equals 1, 2, 3, 4, 5. 5? Yes, that's right. 1, 2, 3, 4, 5. That should be right. Let's see if it's 5. Wait, what do we get? 1 plus 4/5. No. We got to go up to n equals. Wait, n equals 6? Yeah, n equals 6. That's right, because then you'll have 6 minus 1, which is 5. 5 over 5 is 1. 1 plus 1 is 2. There we go. To get you all the way to the end. So here's like A, here's B, and then here are the intermediate points, you could say. All right. Now we're going to plug that into our formula. Remember, each of those intermediate values gets doubled. So this is actually an explicit list of what the sum is going to look like. We have to evaluate the functions at all of those sample points. Again, this is a good time to use a calculator. And since we're talking about this stuff, I really should emphasize now that you will need to use a calculator for this section. And I honestly recommend using a computer or some other kind of computational resource. If you know how to program Excel or Google Sheets, I highly recommend using that because you can pretty easily and pretty quickly just program these formulas into Excel or Google Sheets and then just have it do all the heavy lifting. I know I've talked about it before and we'll talk about it more in the activities and stuff, but there's a very there's a very definite distinction between what a human does and what a computer does. So we'll talk about that more as time goes on. But back to this example, once we compute all these things and we get all these approximations, we get this. So that integral is approximately 1.4908. All right. So now we're going to talk about second order approximations of functions. So we did 0th order, which are horizontal lines. We did first order, which are basically slanted lines, right? Slanted lines. And now we can talk about second order. So second order approximations of a function are quadratic approximations of a function. So in other words, you're going to use a polynomial of degree 2, something that looks like this, and you're going to approximate the function on that interval with that parabola. So that's what this says. Our function is about the same as this parabola on that interval. And like before, it gives us a better approximation of the function than a 0th order or a first order approximation would, but it may not necessarily give us a better approximation of the integral. May not, I'll say. Doesn't mean that it doesn't, doesn't mean that it does, it's just that it may not, and you have to be a little bit careful. All right. Here's another interesting result. So we've talked about 0th, first, and second order. You can approximate functions by a polynomial of any degree that you want. And this is something that we're going to study in detail in chapter 11. That's kind of like the culmination of chapter 11. how do you approximate a function, a differentiable function, with a polynomial? That's pretty much what we study right at the end of chapter 11. So we can use any type of approximation we want for a lot of the functions that we're working with. That becomes like a key point of study later on. So I also want to remind you of this thing here, the Stone-Weierstrass approximation theorem. I know I talk about it way at the beginning of the course, and I talk about it every now and then throughout the course, but remember, this theorem guarantees that if you have a continuous function on a closed interval, that you absolutely can approximate it uniformly and arbitrarily closely by a polynomial. So that's a very, very important result. It just means that if you've got a continuous function, we can find you on a closed interval, we can find you a polynomial that is as close to that function as you want. You just tell us how close is close enough, and we can find you the polynomial. Once we got a polynomial, everything is easy peasy. We can we can approximate integrals, we can approximate derivatives, we can do all sorts of stuff, right? Another thing that some of you might be wondering about, if your data is discrete, meaning not continuous, so imagine your data set is really just like a bunch of points, right? Instead of a continuous smooth curve, you can actually find a polynomial of quote unquote best fit using what's called Lagrange interpolation. And this is actually a really elegant result. So if you want to read about it, just follow that link to the Wikipedia page. But some of you will study this very carefully later on when you take your upper division courses, because it's kind of like the way of approximating a discrete data set with a polynomial, Lagrange interpolating polynomials. So essentially, if you've got a data set, what is the equation of the polynomial that approximates that data set, quote unquote, the best? Probably looks something like this, right? Like that. What's the equation of that polynomial, or what's the formula for that function? That's what these can do for you. That's what those can do for you. Interesting stuff. All right. So now, before we get into the last integral approximation method called Simpson's rule, I want to recall, or at least tell you all about an important property of parabolas. So if you never heard this before, this is an interesting result, and it explains why we need another condition in order to do a quadratic approximation. So any three distinct non-collinear points in the plane uniquely determine a parabola. So what that means is if you just pick any 3 points in the plane that don't lie on the same line, then there's a unique parabola that passes through them. Yeah, ponder that for just a minute here. Let me do that. Any 3 points. And I'll draw you an example here. Okay, so what I mean is if I pick any 3 points that don't lie on the same line, maybe something like this, then there is a parabola that passes through them. It will be a parabola, and that parabola is unique, meaning there's only one parabola that can pass through those 3 points and still actually be a parabola. Maybe it looks a little bit like this. I'm terrible at this. There you go. Maybe it looks a bit like that. But the point is it exists, and you just need 3 points that are not on the same line. But you do need 3 points. So if you have 2 points, you cannot form a distinct parabola. And this is something that I talk about in my pre-calculus class when you start talking about factoring. For example, if I gave you these 2 points, there are infinitely many parabolas that could pass through them. Here's a couple examples. There's one, there's one, there's one, here's one. So you need another point. You need a third point, and when you pick that third point, or when a third point is given, all these other parabolas disappear and your result locks into a single parabola. All right? So you need 3 points to uniquely determine a parabola. Keep that in mind. All right, so we're going to do a quadratic approximation of integrals through a quadratic approximation of functions. So the setup is the same as before. We're going to subdivide the interval up into n equal subintervals. But this time we have to require that n is even. So this is the one difference here. We need n to be even so that we have those 3 distinct non-collinear points. So if n is odd, then we can't actually form the approximating parabolas for every subinterval. So we do need n to be even. Then what we're going to do is on each consecutive pair of intervals, we're going to approximate f by a parabola. I'll show you a picture in just a moment here. Then what we'll do is we'll find the net area under each approximating parabola and sum up the area under those parabolas. And that's what we call Simpson's rule. So this quadratic approximation is known as Simpson's rule. Well, we're not going to do the proof here. This section is already quite long, so I'm not going to fill it with a whole bunch of proofs. But I encourage you to read it on these pages. The proof is there. You can read it and see why this actually works. For us, we're just going to get the intuition and get the formula and use it. So here's the intuition. Let me emphasize something a bit here. Let's see. The curve we're approximating here is pink. So let me highlight it somewhat carefully. Okay, so that pink curve is the function that we want to approximate with parabolas. All right, and the blues are the approximating parabolas. So here's one right there. Notice we needed these 3 points. Actually, let me emphasize that more. We needed these 3 points, P0, P1, and P2, in order to even form that parabola. That's why we need n to be even, because look, here we're using two subintervals, and the endpoints of those two subintervals give us 3 points, and those 3 points allow us to produce a parabola. I guess one thing I should say is that the points do still have to be non-collinear, so they can't all lie on the same line. If they happen to all lie on the same line, then that would mean that you would just have a square or a rectangle for that interval. And in that case, you could basically just pull that piece off and deal with it separately, and then do parabolas for the rest of it. Let me point out the other ones too here. So here's P2, P3, P4. And so we get another approximating parabola right here. And we're just going to find the area under those parabolas. So that's what's going on right there. So we find that parabola, we look at the area under it, and that's actually not so hard to do, right? We could find the area under a parabola equally, or not equally, but precisely, right? That's pretty simple because a parabola is a polynomial. We can just use fundamental theorem of calculus, and so on and so on. All right, so here is the method, or here's the formula for it. Our integral from a to b is approximately equal to s sub n, where s sub n is Simpson's rule applied with n subintervals. So a couple things to point out. Now it's going to be delta x over 3, f of x naught and f of xn, or f sub x naught, sorry, f of x sub naught and f of x sub n are alone again. They only appear once in the sum. But now we get doublings and quadruplings. So it's 4 times that, 2 times that, 4 times that, 2 times that, 4 times that, and it basically alternates between 4 and 2. It will end on an alternation like so, expressly because we picked n to be even. So if n is not even, then you have a problem with the approximation. You won't get this proper, you won't get the right number of terms. All right. So let's use it. Let's use it again. All right, let's use it on that same integral. But now we're going to do n equals 8. So let's let n be 8. Remember, we needed n to be even, so we couldn't use n equals 5 again. We had to pick n equals 8. Just like before, delta x is going to be given by this formula because we're choosing them to be uniform. So 2 minus 1 over 8 is 1/8, and so that's the length of the subintervals. Our endpoints, we're just going to pick the left endpoints again. So we've got this formula to give us the endpoints, and then when you go through and plug I into that formula a bunch of times, you'll get all of your sample points. There we go, all of your sample points. Again, this is one of the reasons that I recommend that you use something like Excel or Google Sheets. You can use a calculator too, it just might get a little bit tedious. But this is a formula that you can quickly and easily program in Excel. And then you can get all these sample points instantly with just like dragging and letting go, and it'll give you all those sample points. All right, here we go. So using the formula for Sn, we get this approximation. Here's the formula, right? Oop, I think I've got a Oh, no, here's the end. Whew, this is a long formula. My bad. There we go. That is what we have to add up. When you approximate those using a calculator or a computer, you'll get these approximations. And then when you add all those up, you get 1.509. There we go. All right, so those are our approximation methods, but I want to speak briefly about just the notion of numerical integration in general. So the approximate integration techniques we've learned here are not the only ones. There are many, many, many different numerical integration techniques. The process that we're doing here is what's called numerical integration. If you'd like to read more about it, just click on that link and go to the Wikipedia page. It's also sometimes called numerical quadrature, and these are often called quadrature rules. So the one thing you want to take away from this is that these are not the only ways to find the area under a curve. These are the ones that we've learned. There are many different ways, and the methods vary greatly, as does their efficiency and the associated errors. So pretty much if you can just imagine an area of any region, think about how you would cut up that region into simpler, like polygons even, and add up the area of those polygons to give you an approximation. That's numerical integration. That's a quadrature rule. So if you can invent one or come up with one, you're coming up with another technique that maybe somebody hasn't come up with before. Uh, the methods also extend to higher dimensions. So if you want to let your brain go wild, just remember that even the things we talked about today, you can extend all of these techniques to higher dimensions. And some of them you will see in Calc 3. So for example, the mechanics of the Riemann integral, when you get into Calc 3, you're still using a zeroth order approximation, but now you're using a zeroth order approximation of a surface in space, a surface, not just a line on the plane or a curve on the plane. Now you're going to have a surface that's in space, and you can approximate it. You can approximate it. All right, but I won't dwell on that too long. Just something to think about for some of you that take numerical analysis later on in your undergrad careers. You will learn a lot of these methods, and you'll probably have to program them as well. But now we need to change gears just a little bit and talk about error bounds. So this is a good place to take a break if you want to take a break. I know it's already been pretty long, looks like about 43 minutes here. So if you need to take a break, just take a break for a minute. I'm going to have a sip of my sparkly. All right, and now let's move along. So each one of these each one of these methods only produces an approximation, right? These are not equalities, these are approximations. And so each one of these has a corresponding error associated with it. And the error depends on the method used, and it depends on the number of subintervals. So tweaking the method and tweaking the number of subintervals changes the error that your approximation has. And a continuing question of interest and an area of current research is the size of the error involved with a given numerical integration method. So if you come up with your own method, for example, how accurate is it? And how big is the error going to be associated with your method that you came up with? And this is something that people still study today. And people try to get even closer and closer error bounds for all of these methods. So sometimes you might not even be able to tell the exact error involved, right? Like you might know that, like you can't say exactly how far off it is, but you can get a bound on how far off it is. Basically saying like, well, the maximum it could be from accurate is this amount. And that's what's called an error bound. Where do you learn about those things? You learn about those things in a course on numerical analysis, like I was just mentioning. Some of you will take a class like that later on in your undergraduate and graduate careers. Numerical analysis is not just restricted to undergraduate mathematics. What we're going to do is we're going to look at the error bounds for all of the methods that we've seen so far in this section. And these are all results from numerical analysis, so we're not going to prove them. I think I say that here. Yeah, I say that right here. The proofs for these error bounds are non-trivial, which means they are not easy. They are not simple. They require a lot of heavy mathematics and heavy machinery and usually a lot of very messy calculations. So we're not going to do the proofs here. Again, some of you will see them later on. But what's nice about having error bounds is we can use these bounds to determine how large n needs to be so that the error is within a certain tolerance. So for example, maybe somebody says, you know what, I don't need the value to be exact, but I need it to be correct to 7 decimal places. Well, a good question is, okay, if you need accuracy to 7 decimal places, how many subintervals do I need to use? How many subintervals would I need to cut up that interval A to B into in order to ensure that the approximation method I use gives me an approximation that's accurate to like 7 decimal places? How do I do that? How do I do that? Well, that's where these error bounds come in. These error bound formulas can tell us exactly how many subintervals we need, or they can give us a bound on how many subintervals, a lower bound. All right, so here's the general idea. In general, an exact integral here can be expressed as an approximation plus an associated error term. That's really what the integral is. The integral is an approximation plus an error. And the exact value of the integral occurs when the error goes to 0. So when the error is 0, then your approximation is exact and you have the exact value of that integral. So each one of our approximation methods has an error associated with it. So we're going to give it a name and define what they are. So E sub t is the error associated with the trapezoidal rule. E sub m is the error associated with the midpoint rule. And E sub s is the error associated with Simpson's rule. And you can see literally that the error is the exact integral minus the approximation. How do you get that? You basically take, think about it like this. Take this term and subtract it from both sides and you get the error, right? So subtract from that and you get integral minus approximation is error. Integral minus approximation is error. That's what it is. We're going to look at the error bounds for the trapezoidal rule, the midpoint rule, and Simpson's rule. That's the ones we're going to look at in this class. So let's explore these a little bit with some tables of values. So we're going to look at this integral, the integral from 1 to 2 of 1 over x. You might recognize that now as a natural log of 2, because this is the integral that gives us the natural log function, right? So we're actually just computing natural log of 2. We're approximating that number. That number is this when I plugged it into my calculator. So my calculator gives me that approximation. Now, if we want to approximate this integral using one of the methods that we learned, we just need to pick how many subintervals. So that's what this is giving us right here. So when n is 5, 10, and 20, these are the approximations produced by the trapezoidal rule and the midpoint rule. So what I want you to do for a minute is just stare at these tables and see what patterns you see. So just take a moment and see if you can see any patterns. All right, now let's talk about them together. Let's see. So here we can see that they're both getting better and better as n gets larger. That's good, it's supposed to do that. Now let's look at these errors. So the error with the trapezoidal rule and the midpoint rule seem to be somewhat related. You see how like this number is twice this number, right? This number seems about twice that number. This number is about twice this number. So there seems to be some kind of factor of 2 involved. Also, the signs are opposite. The signs are opposite. So the trapezoidal rule, we have an opposite sign here compared to the midpoint rule. But this already gives us a pretty interesting insight into things, right? Which is the error associated with the midpoint rule is actually smaller in size than the error associated with the trapezoidal rule. You see that? Let's go to the next slide. I have some notes about it here. Oh yeah, I said this one already. The approximations get more accurate as n increases, but the size of the error when using the midpoint rule is about half the size of the error when using the trapezoidal rule. This is an interesting result because it says that even though the trapezoidal rule is using a higher order approximation of the function, that is not necessarily giving us a better approximation of the area under that curve. So just because you can approximate the function more closely does not mean that you're going to be approximating the area under that function, under that curve, more closely. And that's what these results are telling us. So in this case, the midpoint rule is actually more effective than the trapezoidal rule when it comes to approximating integrals, right? When it comes to approximating integrals. And we can see that there we go. We can see some patterns in the results, right? So we've got opposite sign. Midpoint rule seems about twice as effective with the same number of subintervals, and so on and so on. So let's see what the actual error bounds are. Boom. So this is the error bound for the midpoint rule, and we're going to talk in detail about these for a minute here. If there exists a positive or non-negative number k, such that the size of the second derivative of f is bounded above by k for all points in that subinterval, then the error associated with the midpoint rule has to be less than this value in size. Okay, so this is another one where I want you to stare at it for a minute. I'm sorry I don't have any examples for you to practice so much in this particular section. There's just a lot to think about in this section. So look at this formula for a minute, and then I'll elaborate in just a moment. All right, here we go. So what this formula is giving us is it's giving us a bound on the size of the error associated with the midpoint rule. So basically, if you perform a midpoint approximation to approximate an integral, then the error associated with that approximation has to be bounded by this value right here. Notice it depends on a couple of things. It depends on n. It depends on the number of subintervals, of course. It depends on the length of the total interval, which also makes sense. And it also depends on this number k. We're going to talk about k some more in a minute, but k is literally an upper bound for your second derivative. All right, now compare this to the error bound for the trapezoidal rule. So same idea, we have this upper bound, but now it's for the trapezoidal rule. So everything is the same, but look at the difference. Now, instead of it being 24, it's 12. I'm going to flash back and forth here. Midpoint rule, trapezoidal rule. Midpoint rule, trapezoidal rule. Midpoint rule, trapezoidal rule. So that, that higher efficiency or higher effectiveness of the midpoint rule is manifesting in the formula for the error bound. In other words, we can see the fact that the trapezoidal rule is not as good as the midpoint rule is at approximating an integral. So it's not just something you can observe. Like, we can literally prove it, and we can prove it precisely using this thing. Okay, so let's talk about some of the details here. Let's compare both of these. Like we said, midpoint rule seems to be better. The number k is an upper bound on the size of the second derivative. And this tends to be where students get the most confused, is this number k. K is literally just an upper bound on that second derivative on the interval you're working with. So for one, it only needs to be an upper bound. It does not need to be optimal. So for example, if you know that your second derivative is always going to be less than 3 on the interval a to b, you could pick k to be any number above 3 or equal to 3. You could pick it to be 4, 5, 6. You could pick it to be a million, right? But the more optimal you choose k, the more accurate the error bound will be. So remember, these formulas, they're just bounding the error. They're not telling you what the exact error is. They're saying that the error can't be any bigger than this in size, right? In size. So we're getting like it's an inequality. It's not an equality, it's an inequality. So the better or more optimally you choose k, the better your error approximation is going to be. Yeah, the error bound is going to be. How do you find a good k? Well, one thing I should say is this: you have to choose k. I'm saying this to you, like, you have to choose k based on the interval, based on the function's second derivative, and the behavior of the function, okay? And finding a good k depends on the function and depends on the interval. So there's no universal choice for k. You just want to pick the you want to pick the smallest possible k that you can, all right? So let's try it. This is a really good example. This is a really good question here. So how large do we need to choose n, in other words, the number of subintervals, to guarantee that the trapezoidal approximation of this integral will be within a tolerance of plus or minus 0.0001? What about for a midpoint approximation? So this is another one where I want you to just ponder it for a minute and think about what it's asking. All right, now what I'm going to do is I'm going to throw up the speaker as well and just say something out loud to yourself. See if you can, talk to yourself or talk to your dog or talk to your kids or the wall or your friends, your family, and just try to explain out loud what you think is going on with this question. All right, and now let's work it out together. So for one, we are trying to find the number of subintervals. So that's one thing. We need to find what n is. We're also given a tolerance. This tolerance is this value here. So what this is saying is that we want to approximate this number so that it is accurate to 3 decimal places, which means the first 3 decimal places agree with what the exact value would be. And we're going to do that for both a trapezoidal approximation and a midpoint approximation. So we're going to do both. All right, so if we want to find a bound on the error, or if we want to be able to determine how large n is going to be, we're going to have to use those error bounds. We're going to have to use these formulas right here. But if we want to use those formulas, then we have to compute a second derivative. So that's the first thing we got to do. Luckily, our function is not very difficult to differentiate. It's just e to the negative x. So the second derivative is e to the negative x. So now what we need to do is we need to find an upper bound on this function on the interval from 0 to 1. That's the goal. And once we find that upper bound, that'll be k. That'll be our k value. So here's how we can do it for this case. This function e to the negative x is strictly decreasing. It's strictly decreasing on that interval from 0 to 1, right? It's going like this. So here's 0, here's 1, and this is e to the negative x. So it's strictly decreasing. This is the second derivative. So what that means is that this function achieves its maximum value at 0. So the maximum that e to the negative x will be on the interval 0 to 1 occurs at this point right here. So our second derivative is bounded above by this value, e to the negative 0, which is equal to 1. So this is the largest. This is the largest it'll be. That means we should choose k to be equal to 1, right? We can choose k to be equal to 1, and this is actually the optimal choice of k. You cannot pick k to be any smaller. If you pick k to be smaller, then what you're picking a value that is not going to guarantee that the second derivative is always smaller. So you can't pick anything less than 1. You could pick values larger than 1. So even though we found an optimal k, you could pick 2 or 3 or 4 or 5 or 10 or a million. But when you do that, it's going to make the error bounds the wrong size, you could say, not as accurate as it should be, not as optimal. We'll see in just a minute here. But now that we know what k is, here's what we need. For the trapezoidal rule, we need the error associated with it to be smaller than 0.0001. Okay, this is the first thing to realize. Remember, this formula is the error, and this is the tolerance we were given. Cannot be more, can't be off any more than this amount. So here's the formula for trapezoidal rule. We're going to plug in what we know. We chose k to be 1. B minus a is equal to 1 because it's 1 minus 0. And n is what we're solving for. We don't know what n is. There we go. So now we have everything here except for n, and we just have to solve for n at this point. So simplify this side. I'm going to write it as 1 over 10 to the 4th, just because it's easier to work with fractions, I think. That means that 12n squared has to be greater than or equal to 10 to the 4th. N squared has to be greater than or equal to this. Take the square root of both sides, and you get this. One thing to note, we do not need to include a plus minus in this case because n is a positive integer, so it must be the positive result. And then we need to get an approximation of this. So what I did was I plugged this into my calculator and it gave me something like this. So we need n to be greater than or equal to 29, just like that. Okay, now there's a couple notes or a couple comments I want to make about this calculation. For one, we had to pick n to be an integer because n is supposed to be the number of subintervals we have to use to get this approximation to be accurate enough. So n can't be a rational number, or I shouldn't say it can't have a how do I put it? It can't have a fractional part. It can't have a fractional part. It's got to be an integer. Also, because we need this, we need the error to be smaller than this value, we're going to have to choose n to be the larger number. So we can't round down. We have to round up. If we round down to like 28, then we're not guaranteeing that we'll be within this bound, right? And that's because specifically we need to pick a bigger n. We need to pick a bigger n. Let's see, what else did I want to say here? Oh, I wanted to say this too. Notice where k came into play. So if k came into, if you chose a different value for k, if you chose k equal to 2, 3, 4, whatever, then this number would not be 1, it would be 2, 3, 4, whatever. So let me kind of put this in here. Pretend this was, let's say we chose k equal 4 instead. So if k is 4, then this would be a 4, right? And then this would be over 4, and then this would be 4,000 or 40,000, and then this would be 400, and then what happens is you end up with a larger value of n. You end up with a larger value of n. N has to be bigger than some other number. And so this is what I mean by k equals 1 is the optimal choice. K equals 1 is the optimal choice because from that choice we can get literally the minimum number of subintervals that we need. Minimum number of subintervals. But if you choose a larger k, it just means you're gonna have to use more subintervals than you really need to use. You don't really need to use more than 29. 29 is the best. But if your k value is not optimal, this might be something else like 40, 42, 43. So again, it's not wrong. It just depends on your application, right? It depends on the context in which you're using these results. So you got to be conscientious of that. Another thing I'll point out is this. Notice that the formula for the error has to be less than the tolerance given. So just keep in mind that this is the error. That's the bound on the error, and we need that number to be smaller than this. Okay, that's why the orientation is this is less than or equal to that. Okay, now let me erase these. Let's compare it to the midpoint rule, and we'll see an interesting result. This is the calculation for the trapezoidal rule. This is the calculation for the midpoint rule. So most of the calculations are the same. It just starts to deviate once you get over to right about here. Yeah, right about here. So I'm going to flash back and forth a couple times. There we go. Trapezoidal, midpoint. Trapezoidal, midpoint. Trapezoidal, midpoint. But check this out. Using the midpoint rule, we only need 21 subintervals. 21 subintervals. So this method is more efficient or more effective, you could say, because you don't need to do as much work to get the same level of accuracy. Trapezoidal rule required 29. Midpoint rule required 21. And that's what we get. So to answer the question, we would need to use at least 29 subintervals to guarantee that our approximation is within 0.0001 using the trapezoidal rule. And we'd need to use 21 subintervals to make sure that our error is less than 0.0001 using the midpoint rule. There we go. Pretty cool, huh? Pretty cool. So we save the work of computing the value on 8 subintervals by using the midpoint rule. Okay, now we've got one more error bound to explore, and then we'll call it a day. So this is the error bound for Simpson's rule. Notice it's quite a bit different. And again, we can't go through the proofs of these. You will see these later on in a numerical analysis course where you will prove those. But the structure is very similar. So there's still a k, and we need our second derivative. Oh, wait, hold on a second. Hold on, I believe that's a typo. Hold on a minute, please. Wait a minute, wait a minute, wait a minute. Hmm. 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 I gotta pause here for a second. I feel like there's a typo in this formula. Give me 1 second here. All right, I'm back. Okay. Yes, there is an error in this slide, so I apologize. I'm gonna fix it right now, and then I'll fix it later in the slides. This should be a 4. So what we need is we need this. We need the fourth derivative of f to be less than or equal to k. So I do apologize for that. That should say the fourth derivative, not the second derivative. I knew something seemed off because we needed a higher derivative. Because remember, Simpson's rule involves parabolas. And that's why we needed a derivative that is higher than the second degree or higher than second order, right? So there's a connection between which derivative you need to compute and the error bound. So that's why we needed the second derivative for the midpoint and trapezoidal rules, but we needed a higher derivative for Simpson's rule. So I do apologize. Luckily, it doesn't actually affect the rest of the slides. Let me set this down. It doesn't affect the rest of the work because we're still going to get to choose k optimally. Again, the function that we use this on is nice enough that it just happens to work out. So let's take a look here. And then I'll fix the slides later. Okay, so let's compare the midpoint rule to Simpson's rule. So here are the midpoint approximations. Notice here I chose n to be even because in order to do Simpson's rule, you need to have an even number of subintervals. So this is what we get using midpoint versus Simpson's. And here are the errors. Check out the difference here. Check out the difference here. Error associated with the midpoint rule using 4 subintervals versus Simpson's rule using 4 subintervals. And already the error is orders of magnitude smaller when we use Simpson's rule, right? Compare this number to this number in size. Quite a big difference. So Simpson's rule is much, much more efficient than the midpoint rule, and the errors associated are already very small. So it's a more effective method. But you might be wondering, like, well, if it's more effective, why not just always use it? Well, it's kind of hard to always use it because we require some more things in order to use Simpson's rule. For one, like I was saying, we actually require uh, if we want to know an error bound, we need 4 possible derivatives. We need our function to be 4 times differentiable in order to even talk about error bounds. So that's one thing already. We also need to compute parabolas, right? So we're trying to compute approximating parabolas for the function, and that can be intensive. It might require more work than just computing a simple line, right? It requires more calculations for sure. Okay, so now let's do the same thing before, as we did before. Now we're going to use Simpson's rule to approximate this. And we want to know how many subintervals we need so that it's within a tolerance of 0.0001. Oops. Oh yeah, I say it right here. So just like before, we can take k equals 1. The reason for that is when you compute the fourth derivative, let's see what we get. Let's just do it real quick. So f of x is e to the negative x. F prime of x is negative e to the negative x. F double prime of x is e to the negative x. Third derivative of x is negative e to the negative x, and then the fourth derivative of x is e to the negative x again. So again, we're using the same thing that we had before. So e to the negative x is a strictly decreasing function on the interval 0 to 1. So we just plug in 0 for x and we get e to the 0, which is 1. So we can choose k to be 1 again, and that's an optimal choice. All right, so what do we need? We need that error to be less than this tolerance. So that means this formula needs to be less than that tolerance. We plug in what we know about k. We plug in b minus a, and then we do some algebra, right? Move things around, we get this, calculator approximates this, and then we have to choose n greater than or equal to 4. All right, so first off, let's just think for a moment about how much nicer this is. So remember with the trapezoidal rule, we needed 29 subintervals. With the midpoint rule, we needed 21 intervals. With Simpson's rule, we only need 4. We only need 4 subintervals to make sure that our integral approximation is within a tolerance of 0.0001. Pretty nifty, right? Way, way, way more efficient. You only have to do this 4 times. Another small note I want to make, the reason that I had to choose n greater than or equal to 4 is because in order to use Simpson's rule, you need n to be even. Remember, you need n to be an even number of subintervals. So we can't choose n equals 3, even though 3 is the next larger integer. We have to choose n equals 4, because that's the only way we can actually use Simpson's rule. All right, so now let's do a total comparison. Total comparison. 29, 21, or 4. Now you can clearly see the effectiveness, right? So Simpson's rule is way more efficient than either the midpoint rule or the trapezoidal rule. It just requires a little bit more from the function itself. If you want to get a good bound on the error, you need your function to be 4 times differentiable instead of just 2 times differentiable. All right, on that note, whew, let's take a break. Let's take a break. We will explore these ideas when we do the activity for these. I know this was a long one, so thank you again for bearing with me and staying focused and learning these things with me. Not all the lectures will be this long, but every now and then there's a lecture where you just have to spend like a good hour and 10 minutes talking about it. So I'll stop rambling. Thank you again. I will see you next time.